Okay, so we'll get started. Okay, so let me just recall where we were at last time, because I had started to prove something, but then sort of unceremoniously realized I hadn't set myself up correctly for it. So let me just say what we did prove, and then I'll explain sort of where the proof I had planned went wrong, and then we'll go over a few other things, and then we'll go back and sort of fix the proof for the second half. So at the end last time, we showed and so we're talking about the existence and uniqueness of finite fields, or unique isomorphism of finite fields of order of degree p to the d. So for every prime power, there exists a field with sort of order that prime power, and that field is unique up to isomorphism. And so what we showed last time was if F is a finite field with size p to d, and F, well, we already know it contains Fp, and we showed that if this is true, that if F has size p to d, then F is an extension of Fp, and F is a splitting field for x to the p to the d minus x. Okay, great. So we showed this. And so in particular, once you know that, and once you know that a field of order p to d exists, this gives uniqueness up to isomorphism, because we know splitting fields for some fixed polynomial are unique up to isomorphism. So we still need to see that the splitting field of x to p to the d minus x is a degree d extension. So, and we need to show this splitting field actually is a degree d extension. That will give us existence of such an extent of a degree d, of a field of order p to the d. So, and what do we know? Well, we know that a splitting field for this polynomial exists. Well, okay, and so anyway, sort of what I thought I had planned for last time was then some deduction of the fact that it had size p to d using the structure of the groups of units, using that this was cyclic. So that's why I sort of proved that lemma beforehand. But well, anyway, I'm not sure what I had in mind, but I made some mistake, and it doesn't seem like what I had in mind was going to work out. So sorry about that. So I've been trying to avoid introducing, somehow I'd wanted to prove this fact before introducing more technology. But then there's an easy proof of this fact once we introduce some more technology. So the idea of how we'll do this is we'll just take the splitting field, and we'll show, and well, that splitting field might be, it's not too bad to see that it's at least a degree, at least d extension, but it could sort of a priori be bigger. And then we'll just look and we'll see that there's and yeah, so we'll explain that there's the subfield, like we'll explain that the elements that are the roots of this polynomial actually form a subfield, and then that will give us that so that subfield, somehow that subfield has to be equal to the splitting field itself then. Okay, so that's where we're going to get in terms of that proof today. So that's how we'll rescue me from the end of class last time. But before getting there, we're just going to, there are a couple of concepts that we'll need more generally that we'll use here. So we're just going to do sort of the more general concepts first, and then we'll come back to this. So, so before finishing this, we'll introduce separability. So this is something I sort of very briefly said at the end of last time as I sort of flailed, but let me do it more carefully. So separability of polynomials and the Frobenius map. Okay, so let's start with separability. And so this doesn't start out having anything to do with finite fields. This is just a general notion. So if K is a field and F is a polynomial of coefficients in K, then F is called separable if it does not have any roots of multiplicity greater than 1 in a splitting field. You could replace the word splitting field with sort of algebraic closure here, or you could replace the word splitting field with sort of any field where F sort of factors into linear factors. So you get equivalent notions. The reason being just that, I mean, this says a splitting field, but splitting fields are unique up to isomorphism, and not just isomorphism of abstract fields, but isomorphism of extensions of K. So since A2 splitting fields are unique, so differ by, are isomorphic by an isomorphism fixing K, that means sort of such an isomorphism sends roots of F to roots of F. So you only have multiplicity greater than 1 in one splitting field if you have multiplicity greater than 1 in any splitting field. Okay, so this means let me specify what I mean by multiplicity greater than 1, I guess. So this means, well, in the splitting field, f of x is going to factor is sort of x minus alpha 1 k1, and so yeah, this just literally means write down factorization to linear factors, and then this, so what this is saying is that so multiplicity greater than 1 just means so alpha I, let me say this way, it has multiplicity ki. So saying you don't have any roots of multiplicity greater than 1 is just saying that in a splitting field, F has as many roots as its degree, and as many distinct roots as its degree. Here, alpha I is not equal to alpha j. Okay, so that's simple enough. And that's the definition. There's a nice observation we can make that sort of eliminates this issue of like, this sort of funny issue of like saying a splitting field. And you can actually characterize this. You can actually characterize this sort of purely in terms of this ring K brackets X. So sort of purely with polynomials over K without sort of introducing a splitting field. So let me say observation / lemma. So F is separable if and only if the ideal generated by F and F prime is 1. So this means the ideal generated by F and F prime is I mean, f and f prime are co-prime. So here f prime, so if f is equal to a0 plus a1x, so on, plus an x to n, then f prime just literally means the formal derivative. I mean, we have some, of course, you can't do calculus per se over an abstract field, but the formula for the derivative of a polynomial still makes sense. And so you can still write this down. So f prime is equal to just a1 plus a2 plus 2a2x plus, you just sort of 3a3x squared plus n a n x to n minus 1. So you just differentiate this like you'd sort of differentiate a polynomial over the real numbers. And that's still, and this formula still makes sense is the point. Okay. Okay, good. So let me leave this as an exercise, or you can look in the book to prove this, and I'll just say maybe out loud what the point is. I mean, somehow, if you use this formal formula for differentiation, then you can check, I mean, either by hand, like just by doing the computation, or there's also a purely formal argument you can make and that you can think about that sort of deduces it from the transcendental case. But anyway, and you can deduce one way or another that the chain rule for differentiation still holds. And I mean, somehow this definition is compatible. Like if I think of f as being in k brackets x, or I think of f as being sort of in L brackets x for L splitting field, like this formula stays the same for differentiation, but then sort of I can also, if I'm in a splitting field, then I can sort of factor f into linear factors, and I can take the derivative, and then, I mean, I'm taking the derivative formally, and it's not, yeah, it's basically not hard to see that when you take this, when you apply the chain rule here, like you're going to get something that has no zeros in common with f, unless, yeah, so if it's separable, so if all these ki are multiply 1, then you get something that has none of the same zeros as f. So you just apply the chain rule. So you have to check that the chain rule holds, but and the proof is just apply the chain rule in a splitting field. Okay, so that's how you can see that. I mean, this is not so surprising. Like if you think back to like complex analysis or wherever you first saw this. I mean, a different way. And I'm sure you've seen at some point in your life that you can sort of see the multiplicity of a root by sort of checking how many of the derivatives vanish at that root. But in like if f and f, like if f and f prime have a common zero, then there's no way they can be co-prime, because sort of just like if you evaluate at that common zero, like if you evaluate some linear combination of that common zero, you're going to get 0. Whereas sort of this is saying that like saying they're co-prime means there's some sort of linear combination in term over the polynomial ring that gives you the function 1. So again, this is not, yeah, so this is not actually something new. This is just sort of and this statement is somehow just the observation that the thing you knew already about multiplicity of polynomials and sort of how you compute multiplicities using the derivative still holds. Still holds over the. It still holds over an arbitrary field, because in the end it's actually just sort of a purely algebraic fact. It doesn't depend on actually doing any calculus or anything. Okay, so this is useful to know because this gives you a good way, in particular, for understanding when an irreducible polynomial is separable. I mean, so somehow we've been talking about field extensions, so we're most interested in sort of one of the big ways we get field extensions is by like adjoining a root of a polynomial. And so, I mean, somehow of an irreducible polynomial, and so somehow sort of interesting to, and it'll be interesting to us to know when an irreducible polynomial is separable. I'll say more about that in a minute. But let me just write down an example first, some examples. And of course, if I don't sort of impose irreducible, then it's easy to write down separable nothings. So like for example, well, x minus 1 times x minus 2 is separable. Well, at least if the characteristic of k is not equal to 2. No, that's even if the characteristic k is 2, that's fine. 2 is not 1, 2 is 0. So this is separable for any k. And whereas x minus 1 times x minus 2 squared is not separable for any k. And like, so let me say x minus 1 times x minus 2 times x minus 3 is separable for k not equal to for the characteristic of k not equal to 2, but it is inseparable. So an inseparable is just not separable if the characteristic of k equals 2. Because when the characteristic of k is equal to 2, then sort of 1 is the same as 3. So this is actually, if the characteristic is 2, this is equal to x minus 1 squared times x minus 2. If the characteristic of k is equal to 2. So that has a multiple root. Like in x squared plus 1 is separable over the real numbers, just because, well, it's irreducible over the real numbers, but I can just, I could either take its derivative and check its coprime, or I could use that. I know its roots are I and minus I. And C. Or if it doesn't hurt to just check this derivative condition. So I have x squared plus 1, and then 2x plus 1 is, or 2x is the derivative. So these are coprime. I mean, they don't have any common zeros over the complex numbers, so you know they're going to be coprime. If you want to sort of show their coprime by showing the ideal they generate is 1, well, you can just write down literally a linear combination of these that gives you 1, because x squared plus 1 minus 1/2 x times 2x. So 1 times x squared plus 1 minus 1/2 times x times 2x is equal to 1. So then, and this is of course in the ideal generated by x squared plus 1 and 2x. So this is, this is what it means to be coprime. Like it means you generate together the unit ideal. For polynomials, this is sort of equivalent to not having any common roots over an extension, over sort of an algebraic closure, let's say. Somehow, like if you think about the integers and like sort of prime numbers, like this notation in the ideal generated by sort of two numbers is just sort of that ideal generated by the greatest common divisor, and then sort of like this in this classical sort of elementary number theory fact that you can express the greatest common divisor is like of m and n is a times m plus b times n. It's sort of just saying, there's another way of saying that. Okay, so just recalling some things in case these are rough in your head, and sort of why I'm saying the word coprime when I say this ideal is equal to 1. Okay, so these are examples. So far I've written down I've never written down reducible polynomials that are separable and inseparable over any field. And then I wrote down a separable irreducible polynomial over the real numbers. And the reason I haven't written down an inseparable irreducible polynomial is because they're sort of hard to come by. They're not. They take a very specific form, it turns out, and in particular, like over the real numbers or over any field of characters of 0, it turns out there are no inseparable polynomials, no irreducible inseparable polynomials. But you have seen an example on your homework already. So if I look at x to the p minus t over fp parentheses t. So I look at the field of rational functions in a single variable over fp. And I look at the polynomial x to the p minus t. This is inseparable. So we can check both conditions. I mean, if I add a single root, so I can't remember if I did the general case or maybe I just did p is equal to 2 or 3 on the homework. But if I just add a single root, I'm going to write that field as fp t to the 1 over p. So in this field, you can check, and well, we'll do a similar thing later, so let me not check it right now. This actually factors as x minus t to the 1 over p to the p. So you might, well, let's just do it now. I mean, somehow you might complain that this doesn't look like it should be true. But this is true, and this is something special about p powers in fields of characteristic p that we're going to use multiple times today. And if I just expand out this right-hand side, I get, well, x to the p plus, I guess, plus p choose 1 times x to the p minus 1 times t to the p minus 1, t to the 1 over p minus t. Let me say it this way, I'll just do the minus signs out. So times t to the 1 over p plus the p choose 2 times x to the p minus 2 times t to the 2 over p. So t to the 2 over p, I just mean sort of, I take this fixed root t to the 1 over p. This is some fixed root. And then I raise it to the second power, and so on, plus so p choose p minus 1 times x times t to the 1 over p, plus or minus, depending on where p is even or odd, minus plus. I guess it's the minus. Actually, I guess I can always write this. I can always write this as minus or as plus. Well, it's not going to matter in a minute. You can ignore the machinations that were going on in my head there. And this is supposed to be t to the p minus 1 over p. This is t to the p over p, which is equal to t. But the point is all of these binomial coefficients. So here I'm just expanding using the binomial formula, whatever it's called. I mean, I'm just expanding with the standard formula for this kind of thing, using binomial coefficients. And the point is, so p choose I, that's equal to p factorial over I factorial times p minus I factorial. This is divisible by p. So this is an integer. And so that's why it makes sense sort of still in an arbitrary ring. Like this binomial formula makes sense in an arbitrary ring because these are just integers. This is divisible by p, and so it's an integer divisible by p, so it's 0 in fp. And why is it? So this is for 1 less than equal to I, less than equal to p minus 1. I mean, the point is p factorial is divisible by p, certainly. But if you take sort of a factorial for, if you take any number smaller than p and you take its factorial, like that's not going to be divisible by p. And so you're just multiplying together numbers that are smaller than p. So for a prime number p, so these binomial coefficients are divisible by p, except for like the extremal case. I mean, so p choose p is just 1, and that's not divisible by p, and p choose 0 is 1. That's not divisible by p. Okay, so this is just equal to x to the p minus t. So that's sort of justifies this formula, that x to the p minus t is just x minus t to the 1 over p to the p. So in this saying, like actually this field where I just sort of a priori just added one root. So when I wrote fp t to the 1 over p, I literally just mean sort of the field you get by adding a single root. I mean, it turns out this single root is the only root. So this is actually a splitting field. And over this field, the polynomial x to p minus t splits into linear factors, but there's just sort of one linear factor p times. Okay. So something like this was on your homework. I think the one that was due on Tuesday. Or like some example related to this anyway. Good. So this is an inseparable polynomial that is irreducible. I mean, by Eisenstein's criterion, this is irreducible. Okay. So what's the other way we could have sort of verified that this was inseparable? Well, we could use this derivative criterion. And so if f of x is equal to x to the p minus t, then f prime of x. So this is sort of the derivative with respect to x. So when you have to be a little bit careful because you can get yourself confused here, but this is derivative with respect to x, and like everything like in fp parentheses t here is a constant. So like derivative of t is 0. So this is just p times p times x to the p minus 1 times 0, or plus minus 0. And so yeah, so I'll highlight this. This is the constant term. So the derivative of this part is 0. So you just get the derivative of this first part. But in the derivative of this first part is 0 because p is equal to 0 in this field. So the ideal generated by f and f prime is actually just the ideal generated by f in this case. Okay, so good. So that's an example, and this example is really like the only thing that can happen. So let me state. I guess another lemma. You could call this a theorem. Or you could even call it a corollary. Yeah, maybe it's best to call it a corollary. But I guess have I called anything a theorem yet? So if it's a corollary of the observation slash lemma, let me just call it a lemma, I guess. So f, yeah, okay, I'll call this a lemma and I'll call the next thing a theorem. So f is irreducible, sorry. If f is irreducible, then f is separable if and only if f prime is equal to 0. And the proof, f is contained in the ideal generated by f and f prime, which is equal to which is generated by some element d, I'll call g. And f prime, So G, yeah, F prime is equal to G times H for some H. So F prime is also this deal. So that means, so the degree of F prime is strictly less than the degree of F. Right, so the degree of F prime is strictly less than the degree of F. Let me say it this way. It means if F prime is not equal to 0, then right. So if F prime, yeah, sorry. I'll just set this up right. If F prime is not equal to 0, well, I guess we'll just do it like this in cases, then the degree of G, which is less than equal to the degree of F prime, is strictly less than the degree of F. So, but G divides F, because I mean, F is in this ideal, implies G is constant. So, okay, so here's the point. And if F prime is not 0, then sort of the element that generates this ideal, well, in particular, it divides F prime. And so, but F prime, if it's not 0, like just by the formula for differentiation, you have degree less than F. So that means the degree of this generative ideal is less than the degree of F prime. Is at most degree of F prime, and well, that's strictly less than the degree of F. And so you get sort of some you get some divisor of F of lower degree. But that, I mean, F is irreducible. So the only such divisor is the constant function. And so, so G is a non-zero constant, so it's equal to 1. Right, so not that it's equal. This ideal is equal to 1. So that says there. Okay, so that says if F prime is not equal to 0, the ideal generated by F and F prime is the whole ring. F and F prime are co-prime, so that's equivalent by what we said before to F being separable. So and conversely, if F prime, sorry, this is supposed to say F prime is not equal to 0. So the statement is supposed to say that F is separable if only if the derivative is non-zero. So we prove that if the derivative is non-zero, then F is separable. And let me just skip through another. And the other direction is basically running the same argument backwards. I mean, if F is separable, then the ideal generated by F and F prime is equal to 1. It's not even running backwards. So if F is separable, the ideal generated by F and F prime is the trivial ideal. That means F prime can't have been 0, because otherwise the ideal would just be the ideal generated by F. Okay. Other direction easy. Okay, so I mean, and then of course, and this really uses the F is irreducible. And we saw lots of examples where this wasn't true above. When you didn't require F be irreducible. Yeah, this is right. So someone pointed out in the chat this mistake. So this is supposed to be F is separable if only if F prime is not equal to 0. Okay, good. So what does that mean? Well, now F prime X, so if X is equal to A0, a1 x plus a2. Let me just write it this way. Let's write it's the sum from n equals 0 to infinity of a n x to n with the convention that after some n, these are all 0. So f prime of x is then just the sum from n equals 1 to infinity of an, so n times an times x to the n minus 1. And so this is equal to 0 if and only if, I mean, all these coefficients have to be equal to 0. So saying a polynomial is equal to 0 is just saying all of its coefficients are 0. So this means n times an is equal to 0 for all n greater than or equal to 1. Okay, and well, how can n times an be equal to 0? Well, either an is 0 or n is 0, because this equality is 0, then this is taking place in the field K, so it's an integral domain. So in one of like for this product to be 0, one of these things has to be 0. So what that means, when is n 0? Well, n is 0 only if it's divisible by the characteristic. So this is true if and only if an equals 0 for n not divisible by the characteristic p. So here we make the convention that's sort of, a field that has q inside of it is called a characteristic 0. And so we say sort of the only number that is divisible by 0 is 0. So we hear, for this to be true, sort of you should let p to be 0. You should let p be 0, and you should say 0 divides 0. And then sort of that covers also the constant coefficient. Just because f prime of a constant polynomial is always 0. Okay, and we can think that. So, okay, so what's that mean? We've sort of established the following theorem. If you sort of think about what this means, so what this means is if you have an irreducible polynomial that's inseparable, so if you have an irreducible polynomial that's inseparable, then like the only powers of x that appear are sort of powers of the characteristic. So, and just like in our example, like and it was no coincidence, then this example, the only powers of x that appeared were sort of the 0th power of x in the constant term, and then the pth power of x. And we saw when we computed the derivative, that sort of let us get 0 in the derivative. I mean, if p was 3 and we'd had x squared here, then we would have gotten sort of a 2 times x in the derivative, and we wouldn't have gotten 0. So the only way you're getting 0 is sort of when you have sort of all the non-zero coefficients are sort of corresponding to exponents of power of p. Okay, and so we can sort of bootstrap that up a little bit, and we can just say, if the characteristic of k is equal to 0, then every irreducible polynomial is separable. So that means somehow this issue of having multiple roots is like having an irreducible polynomial with sort of a root of multiplicity greater than 1. This is something that can only happen in characteristic p. So like this doesn't happen for extensions of the rational, like for polynomials of the rational numbers. So that's our first point. So if the characteristic of k, so I guess I should be, so every polynomial. So if the characteristic of k is a prime number p, then every then every then if f is an irreducible polynomial, in k brackets x, then there exists a unique separable irreducible g of x in k of x. There's some other separable polynomial g and sort of positive integer k such that f of x is just obtained from the polynomial g by substituting in sort of x to the p to the k for your variable. So I just sort of, e.g., like x to the p minus t is equal to g of x to the p for g of x is equal to x minus t. So this polynomial g is separable, and this sort of inseparable polynomial we were looking at before, I got it by just sort of substituting in x to the p. I mean, so and the converse is not true, I should say. Let me. Okay. So before I talk about the proof, which we've basically already done, let me just say warning. If g of x is irreducible, g of x to the p may not be. So, and for example, if I take g of x is equal to x minus 1 in fp, brackets x, then g of x to the p, so I'll write f of x is equal to g of x to the p is equal to x to the p minus 1. Well, this is not irreducible because this is equal to x minus 1 to the p. So by the same sort of binomial coefficient argument as before. So and the statement is not that anytime you have an irreducible polynomial, if you substitute in x to the p, you get an irreducible polynomial, which is now not separable. The statement is rather that if you have an irreducible polynomial, then it sort of always comes this way. So you can always sort of break it apart into a separable polynomial and then just sort of taking some power of p. And so, and the issue here in this example in the warning was that in 1 has a pth root. I mean, 1 is a pth root of 1. So somehow, the issue is exactly like when the roots of the polynomial already have pth roots in the field. Some version of this. Okay, so anyway, great. So that's the theorem. And it's basically follows from what we just said. So, I mean, an irreducible polynomial has degree larger than 1, or at least has degree at least 1. Like constant polynomials aren't considered reducible. But then in character 0, that means its derivative is non-zero. Like a polynomial of degree at least 1 in character 0 has non-zero derivative. Only constant polynomials have 0 derivative. So that sort of gives this first part. And then the second part just comes from the fact that we saw the only way you can get a 0 derivative is exactly if only sort of powers of p are appearing. So you just take sort of well, you sort of write it as g of x to the p, and sort of then you just apply the same thing to g. Like if g is not separable, then there's some if g is not separable, then sort of just again sort of write some new polynomial g2, such that g is sort of g2 of x to the p, and then keep on going. And the only thing that's sort of maybe not completely clear in this statement at this point is why this polynomial g of x is automatically going to be why this polynomial g of x is automatically going to be irreducible. But if you think about it, you'll see it's sort of it's pretty clear. Like if g of x is reducible, then sort of f of x is also reducible, just because sort of you substitute in the same fact. So if g of x is reducible, then f of x is also reducible. Okay, so that's, yeah, so somehow we've introduced an issue, but then we've introduced this issue that is sort of subtle, this idea that it's subtle and surprising because it's not something you encounter classically, that you could have an irreducible polynomial that didn't have distinct roots. But now we've seen like that, although this can happen, it can only happen in a very controlled way. And we've essentially already seen like the only example in which this occurs. So it can only happen in characters like p, and sort of only when you sort of take some separable polynomial and substitute sort of some power of p in. So, I mean, what this is saying is sort of, the motto is separability of irreducibles and so it has something to do with taking p-th roots in characteristic p. Okay, and so let me not let's see what time and so I'll state the result, and it's not so hard to get from what we've already done, but okay, well, I'll come back to this in a second. So I'll state some result, but I probably won't prove it that makes this statement precise. And before doing that, like we should sort of ask, why is taking roots, like why are p powers special in characteristic p? Well, it's the same, I mean, it's this thing about the binomial coefficients. So it's the fact that the binomial coefficients are divisible by p. And let me sort of package that as a different way. So if k has characteristic p, then that's when they say theorem. The map from k to k, which sends every single element of k, so if alpha is an element of k, this goes to its p-th power, is a ring homomorphism. So a ring homomorphism of fields is a field homomorphism. So well, I mean, this is not true in characteristic 0. Like, note, if I take q to q, I take the map that sends a rational number to alpha squared, like does not satisfy alpha plus beta. So it's not additive. And this is sort of like your calculus students wish was true, but it's not. So this is not true, and it's equal to alpha squared plus 2 alpha beta plus beta squared. and the point is, like, in characteristic 2, this factor of 2 kills the middle term. And so in general, in the proof, and this is taking p powers, like, clearly that respects multiplication. Like, a times b to the p power is ab to the p is equal to a to the p, b to the p. So that's easy. 1 to the p is equal to 1. That's easy. 0 to the p is equal to 0. That's easy. So, the only question is why a plus b to the p is equal to a to the p plus b to the p. And that follows from this thing about binomial coefficients. So this is because this is equal to a plus p choose 1 times a to the p minus 1 b plus p choose 2 times a to the p. So it's supposed to be a to the p. Then all of this goes away because it's divisible by p. Just like in characteristic 2, like when I expand alpha plus beta squared here, this middle term, 2 times alpha beta, is just 0. Okay, so when you're in characteristic P, you have sort of a natural field homomorphism that's sending alpha to the P. So essentially this says, like, P roots somehow behave in P roots and sort of P powers, like, behave in a very different way than roots, like nth roots for some n co-prime to P, nth powers. Okay, and so, well, for example, so here's one corollary of this. So this map has a name. So this is called the Frobenius map, or sometimes the p power Frobenius map. And this applies not just for fields, but you also have Frobenius map, like, for any ring where p is equal to 0. So I'm pretty sure if you have, like, an algebra over a field of characteristic p, you also have a Frobenius map. But sort of in this setting, when Frobenius is a map of fields, just for example, you see 1 is the only root of unity in any field of characteristic P. And so the proof, well, field maps are injective. There's only P root of unity. So this is a map of fields. It's automatically injective, but we already know 1 maps to 1. So good. I mean, another way to see this is the computation we already made, that x to the p minus 1 is equal to x minus 1 to the p. So that says exactly that 1 is only the p root of unity. Another corollary is any alpha containing k has at most one p root, because sort of if alpha to the 1 over p is such a root, then, well, and again, the map, like the p power map, is injective, so it's the only one. But you can also check. I mean, x minus alpha to the 1 over p to the p is equal to x to the p minus alpha. Okay. So let me say sort of a definition / theorem. a field is perfect if every irreducible polynomial is separable. So that's the definition, and the theorem is that this is equivalent to saying, so let me call, so field K is perfect if every irreducible polynomial in K brackets X is separable. So this is equivalent to saying that K has characteristic 0. So that's something we've already seen, that when K is characteristic 0, every irreducible polynomial is separable. And then the thing we haven't quite seen yet, but we're very close to because of this sort of classification of inseparable irreducible polynomials we wrote down, so this is if and only if K has character 0 or the characteristic of K is equal to P, and the Frobenius map is surjective. Which is, and the Frobenius map is already injective, so and saying it's surjective the same as saying it's bijective. Okay, so I'm not going to prove this, but we're not so far because we've already sort of given this theorem, and you can sort of deduce it. You can deduce it from this characterization of inseparable irreducible polynomials. Okay, so good. Let's see. So for example, if F is a finite field, F is perfect. So the proof, just an injective map of finite sets is surjective. So the Frobenius is always injective, and so that's it's in particular a map of sets and an injective map from a finite set to itself. So injective map from a finite set to itself is bijective. Okay. So, I mean, this sort of illustrates why we had to get pretty exotic to write down an inseparable irreducible polynomial. So we had to work over like the field of rational functions, because the simplest examples of like, first, it was never like we're never going to get such a thing in characteristic 0. And even in characteristic P, like you couldn't work over FP, like you have to work over some more complicated field to see an inseparable irreducible polynomial. So, and because of this, a lot of times, so this notion is completely ignored, like in a first class on field theory, like a class in a first treatment of Galois theory, and sort of, this is basically a reasonable approach. But it's good to sort of understand that this issue is out there, and this sort of is more important in sort of. And this is quite important in lots of things, actually. So it's good to be aware. So, okay, it's 1:25. I think. Sorry, I haven't given you a break. I haven't given you a break yet. I think what I'll do is we're almost to the end anyway. So let me just finish. I think I'll go back and I'll finish this proof. So I'll finish this proof from last time now, and then we'll see where we'll either just stop or like come back for 5 minutes, take a break, and then come back for 5 minutes. But we'll probably just stop. So, okay, so I've introduced 2 new things. I've introduced separability, and I've introduced the Frobenius map. And these are the 2 things sort of we're going to put together to see that the splitting field of x to the p to d minus x is a degree d extension. So to sort of see that there is a field of order of size p to the d. So this thing we had left over from last time. Okay, so let F be a splitting field of x to the p, so F, extension of FP. It's the splitting field of x to the p to the d minus x, which is a polynomial in sort of FP brackets x. Okay, so I'm going to show that F is degree d over FP, which is the same as saying, so this is something we've already seen, that, and this is the same as saying that the size of F is equal to p to the d. Okay, and so how do we do that? Well, first, so step 1, so what I want to do, so step 1, I want to say right. If I look at the derivative of this polynomial, this is equal to -1, which is non-zero. So it has p to the d distinct roots. Sorry. So sorry, this derivative is -1. Sorry, I was being a little blasé there. So that means the ideal generated by it, and so this polynomial is 1, and thus it's separable. Okay, so if I take this derivative, I get -1, and this first term goes away, I just get -1. And then I take the ideal generated by F and its derivative, well, that contains 1, so it's ideal generated, it's the whole ring, which is the definition of separable. And what I said, so what I just said was not quite right. I said, I had just said that this was non-zero, so it was separable. Like that's what I wrote first. But of course, this polynomial is not irreducible. So it's not enough to say, like, since this polynomial is reducible, it's not enough to say that this derivative isn't 0, so it's separable. Like you have to say that you really have to check that sort of the polynomial and its derivative generate the whole ring. That's the idea. Okay, but it does, and it's still easy to see that. So this has p to the d distinct roots. Okay, and then the next claim is that the set sort of alpha such that of all alpha and f such that alpha to p to d minus alpha is equal to 0. So the set of all roots of this polynomial is a subfield. Let me say this is alpha to p to d is equal to alpha. This is a subfield. Okay, so these are sort of This is all roots of x to the p to the d minus x. So, and this is a set. So this has size p to the d by the first part. And I mean, it also contains all these roots. So if this set is a subfield, then it's actually equal to f, because f is supposed to be a splitting field. So sort of f is supposed to be the smallest subfield that contains all the roots. So if the set of all the roots is itself a subfield, like it has to be equal to f. So if I can show this, then that really shows that this shows what we want. Okay, and this is we could say it more concretely, but let me just say it as part of an abstract statement. So note, like alpha to the p to the d is equal to frob p composed with frob p. Like I take this field automorphism, I compose it with itself d times applied to alpha. So, I mean, if I take frob p, this field automorphism, this just sends, well, first it sort of sends it alpha to the p, then it sends alpha to the p to the alpha. So this is alpha to the p to the p to the p, and so on. But in sort of to bring in a p from top, you just sort of square it. So this is equal to alpha to the p to the d. So okay. So we call this sort of frob sub p to the d. Just this d-fold composition. It's just the map that sends alpha to the p to the d. But this is a field automorphism. So it is an automorphism of f. And if you start with one automorphism, you just compose it sort of however many times, like what you get is still an automorphism. Okay. And then sort of saying alpha p to the d is equal to alpha is just saying frob p to the d of alpha is equal to alpha. I.e., you're saying alpha is fixed by frob p to the d. Okay, and so now, easy check. Sort of if K is any field, and sigma from K to K is any automorphism. So an automorphism just means it's a ring homomorphism from itself to itself. It's bijective. Then the subset of elements in K such that sigma of K is equal to K. Sigma of little k is equal to K. Little k. So the subset of things fixed by this automorphism is a subfield. I mean, somehow this just follows from the fact that like an automorphism respects the field rules. It's like sigma of alpha plus beta is sort of sigma of alpha plus sigma of beta. So it preserves things that are fixed. Okay, so applying that here, you get that. So the things that are fixed by this p to the d power Frobenius automorphism form a subfield, but those were exactly the roots of this polynomial x to the d p to the d minus x. Okay. Good. So that finishes showing that the splitting field has degree d, because we've shown it has p to d elements. So it shows, and we've actually directly shown that it had p to d elements in it. Okay, so that's what we wanted to do. And so now let me just say, I mean, somehow this this construction right here, the fact that if you take an automorphism and you look at sort of its fixed field, what you get is a subfield. Like this is sort of one of the things that lies at the heart of Galois theory. So this is sort of a phenomenon we're going to investigate more generally next time. But you're right, yeah, so still haven't taken that break, so let's just stop here. I'll stop, but I'll stick around if anyone has questions. And sorry we didn't do a break today.